Hello everyone, today let's take a look at QP 101 in which we've rolled two fair 30-sided dice and we're looking at the top faces of them. These rolls are independent and each side is numbered from 1 to 30. So what is the expected value of their absolute difference? So let's let z be a new random variable and that's just going to represent the absolute difference between x and y. And no, I cannot use linearity of expectation here because this absolute value function is not linear, right? It looks like this. So if I just take the definition of expected value here, the expected value of z is just going to be equal to the sum over all the possible values that z can take of this function right here, x minus y, and then times the probability that z is equal to little z. Well, I can't distribute this right here inside of this absolute value because it's not linear, right? If there's no absolute value, then I could, and then obviously the expected value of x minus y would just be equal to 0 because they are coming from the exact same distribution. So again, can't use linearity of expectation because this is not linear, so we're going to have to do it the old-fashioned way. First of all, what are the possible values that this function could take? Well, x could be between 1 and 30, and so could y. So the absolute difference between them at most is going to be when one of them is way higher than the other one, right? So our maximum is 30, our minimum is 1. So the absolute maximum that our difference could be is 30 minus 1, which is going to be 29. So this is the maximum value that z can take. And now what's the minimum value? Well, we know that the absolute value is always going to be greater than or equal to 0. And when x is equal to y, well, then we're going to get 0. So our minimum is 0, right? So we can rewrite this to reflect that. You can see z is going from 0 to 29, the possible values that the absolute difference can take. And now we just need to figure out this over here, the probability distribution. We can just do that using some combinatorics. So first of all, what is the probability that z is equal to 0? Well, the total number of outcomes for two fair 30-sided dice that are independent are going to be 30 values for the first one times 30 values for our second dice. That's going to be 900 total possible outcomes. And the only way that z could be equal to 0 is if we get one number for our first die and then we get the exact same number for our second die. That's the only way the absolute difference between them can be 0, obviously. So for instance, right here, if I get two 14s, the absolute difference is going to be 0. If I get two 15s, the absolute difference is going to be 0. So what's the probability of getting two of the same number? Well, basically, for my first die, I obviously have 30 different possible outcomes, 1 all the way up through 30. And then once that is fixed, well, then I only have one possible outcome that makes it the exact same value that I got before, right? Therefore, 30 outcomes for my first die, 1 outcome for my second die. There's going to be 30 combinations of the exact same number appearing. So there's going to be a 30 out of 900 chance that z is equal to 0, right? Now let me just erase this and let's look at the probability that z is equal to 1 and try to find some type of pattern. Well, if I want z equal to 1, that means the numbers are 1 apart. So I either have 1, 2, or maybe I have 2, 3, and then maybe I have 3, 4, 4, 5, all the way up to 29, 30, right? So these are all the possible roll combinations that have a absolute difference of 1. Now for this roll combination right here, where one of my dice is a 1 and my other dice is a 2, well, dice 1 could either be a 1 or a 2, so it is two different options. And then once I've chosen that option, I'm going to have 1 remaining for the second die. Now for this roll combination, my first die could either be a 2 or a 3, and then my second die is just going to be whichever other one is remaining. So I have 2 options for my first die and 1 for my second, and same for all of these different roll combinations. Now I have 29 different total roll combinations with an absolute difference of 1, and for each of those, I'm going to have 2 ways to distribute it to my dice. So my probability of getting an absolute difference of 1 is going to be 2 times 29 and then divided by our total number of outcomes, 900. Now let's look at the probability that z is equal to 2. So the absolute difference between the dice is 2. So I take the probability z equals 2. Now again, let's look at the roll combinations between 1 and 30 such that the absolute difference between them is 2. Well, I have 1 and then 3, or I have 2 and then 4, 3 and 5, all the way down to 28 and 30. Now for each of these distinct pairs of numbers, I have 2 possible options for my first die and then 1 for my second die. For this one, when I have a 2 and 4, I could either give a 2 or a 4 to my first die, and then the other one is going to be fixed. So I'm going to have 2 ways to distribute all of these different combinations. Now again, you can see I have 28 different pairs of numbers such that the absolute difference between them is 2, and for each of these I have 2 ways to distribute them to my dice. So my probability is going to be 2 times 28 out of 900. Now you can see the pattern. If now I were to find the probability that z is equal to 3, well, we list out our pairs of numbers again. I can have a 1 and then a 4, or I could have a 2, 5, 3, 6, and now I'm only going to go up to 27 and 30, right? Now I only have 27 pairs of numbers that satisfy this absolute difference of 3. You can see that as I increase this absolute difference, I'm going to be getting less and less pairs. There's no more 28 as my lower number in the pair, right? If I roll a 28, well then the only other way that I could get an absolute difference of 3 is going to be if I have 25, right? I can't roll a 31, so I'm reducing my number of pairs as I increase this. And again, for each of these combos, I have 2 ways to distribute it to my dice. So the probability that z is equal to 3 is just going to be, again, 2 times, this case, 20 27 on 900. Now you can really see the pattern. So if I increase z all the way up to its biggest value, z equals 29, well, there's going to be only one combination of numbers that satisfy this absolute difference, and it's going to be 1 and 30, and I have two different ways to distribute this among my dice. So I'm going to have a 2 times 1 on 900 chance of rolling this absolute difference. So we can come up with a formula for our probability distribution. You can see that as z increases by 1, this number is just going to decrease by 1. The only outlier was the probability that z is equal to 0. There's only 30 ways to do that, but that doesn't even matter because we basically, when z is equal to 0, this whole term is going to be 0, so we don't even have to think about that. So the probability distribution from z going from 1 to 29 is just going to be 2 times 30, you can see, minus the value of z divided by 900. So does this check out? When z is equal to 1, we're going to get 29 here, which checks out. When z is equal to 2, we're going to get 28 here, checks out. When z is equal to 29, we're going to get 30 minus 29 equals 1, and that checks out as well. Okay, so now we can just plug this in. Remember, we can disregard when z was equal to 0, so we just start z from 1 and we go all the way up to 29 of z times this probability distribution right here, or the formula for it, which is 2 times 30 minus z on 900, like so. Now I can pull out my constants, my 2 on 900. Let's just pull those over here. So I have 2 on 900, which is just 1 on 450 times, I'm going to basically distribute this inside. When I do that, I'm going to get 30z and then minus z squared. Now I can split this up into two different sums. So I'm going to have 1 on 450 all times the sum from z equals 1 to 29. I can just pull a constant of 30 out front here. So 30 times z and then minus the sum from z equals 1 to 29 of z squared. Now from QP65, we know the series summation formulas for both z and z squared when we're just dealing with the first n natural numbers from 1 all the way up to 29 in this case. Now from QP65, we know this formula. In this case, n would be equal to 29. So we take n times n plus 1, which would be 30 in this case, and divide that by 2. And again, also from QP65, we know this formula as well. We take n, in this case is 29, and then we multiply that by n plus 1, in this case 30, and then we multiply that by 2n plus 1, so in this case 59, and then we divide that all by 6. I'm going to cancel a 6 here with a 6 from the 30, and then we're going to get a 5. 29 times 30 is 870, so when we divide that by 2, we get 435 here, and then when we calculate this one, I'm going to get 8555. Now let's plug these back into our equation. I have basically 1 on 450 times 30 times this number right here, so 30 times 435, and then we also need to subtract off this number, which was 8555. Okay, when I take 30 times 435, I get 13,050, and then when I subtract off 8,555, I'm going to get basically 4,495, and then that's all going to be divided by 450. Now to get this in lowest terms, I can divide both top and bottom by 5, and when I do that, on top I'm going to get 899, and on the bottom I get 90, which is going to be in lowest terms, and this is roughly 10. It's pretty close to 10, 9.98. So yeah, just using definition of expected value here, not many tricks that we can use like linearity of expectation, we just have to do it straight up.